All right, so that has given you a pretty good idea of what technology choices can you basically make when you're designing your resonator. So let's say you have basically have decided to design and build a resonator, or you're considering a resonator. The next natural question is, how on earth do I know my unloaded Q? Somehow I have to be able to load this with signal, with an excitation, and basically get information that I want. So here's how it works in a schematic fashion. So your resonator is represented by this equivalent RLC in this particular schematic. What we need to do to measure this unloaded quality factor is to feed this resonator with some energy. So that is essentially what this coupling does here. So we will excite this with some type of a source, and then we basically couple this energy to our resonator. And then the same way here, we will basically have a coupling at the at the second port, at the output, and basically measure this energy that goes to our load. There are essentially two equivalent ways you can do that. The one I just explained, but there's also this way where we can basically have a direct through line from my source to the load and essentially take energy out from this parallel path. Now, in order to derive some equations and that we can basically compute our coupling and the quality factor, it is important to very clearly define in our minds the three different quality factors that we have. So the first one is already defined, which is the unloaded quality factor. So once again, the unloaded quality factor simply measures how much energy is being lost in the resonator itself. So naturally, and I'll go back to this figure, it should really depend on just the resistance of the resonator itself. And indeed, if you could ideally measure this quality factor, it basically would get the equation that you see right here. It only depends on the resonator resistance itself. Now, the second quality factor is this external quality factor, which essentially means it's the quality factor that measures energy storage versus energy dissipation, but the energy dissipation is caused by the loading impedance only, which, because it's external to the resonator, we call it external resistance. And so that means that now my external quality factor is only due to the existence of the external resistance. That is the resistance, for example, that you will have right here by loading the resonator from the input and from the output. Finally, you have what we call the loaded quality factor, which is the quality factor you get when you measure this in real life. Because in real life, the losses come both due to the resonator itself as well as to the loading resistance. So the loaded quality factor is actually given by this equation, and that's the quality factor you can directly measure. That's the quality factor that is basically measured by taking the center frequency and dividing it by the bandwidth, as we discussed in the very beginning. But what I really want is this. In other words, what I really want to know is the quality of the resonator itself without being influenced by my loading circuitry. So the unloading quality factor is the true metric without being loaded by the external circuitry. It's kind of the same way when you buy a car, you want to know the mileage in this car in the best case scenario, meaning without considering a bad driving habit that somebody might have that may actually ruin the mileage. The mileage of the car could be great, but if the loading resistance is bad, then you might lose energy, but not because the car itself is not good. So here's basically how the equations work out for the loading case I showed you before. To make things simple, I will assume that my ZS is real, I will assume my ZL is real, and I will assume that the coupling sections are basically equivalent. So if I do that, you will basically find out that the external resistance that you see is basically given by N square RL RS over RL plus RS. That is basically the external resistance that you will see when you measure that circuit. So under those conditions, you have this very well-known equation that basically tells you that essentially Q unloaded, which is what you need to measure, and Q external are essentially connected in parallel. Now, if you do a very simple analysis in this circuit, you will basically find out this very well-known equation that the Q unloaded is equal to the loaded Q, and remember this is what you're actually measuring, over 1 minus S21 at F naught, the center frequency of your filter. So in other words, because you can basically measure QL, that's nothing else but the 1 over the fractional bandwidth that we basically discussed before, you can directly know the Q unloaded if you can only measure this S21. But there is a trick. And the trick here is that even though in principle this measurement will work for any value of S21, ideally you would like this S21 number to be actually a small value. You don't want, when you make this measurement, for your S21 to be essentially close to 1. Because if the S21 ends up being close to 1, then this number here is actually going to be approximately 0. And that's bad because any measurement error you make in the S21 will automatically translate to a big measurement error in Q unloaded. So once again, even though it's possible to use this equation to derive your Q unloaded for any level of S21, the real world measurements always have S21 at very low levels. And in fact, the lower the level, the better. Maybe S21 will be in the order of 20 dB, will be 30 dB. And of course, that 1 here is the 0 dB. So if that's the case, if this S21 number is basically much, much less than 1, then this equation actually holds here. And in fact, this is what we normally do in real life. We normally will design our circuitry such that the S21 is much less than 1. And once we achieve that, then we will simply directly measure the loaded quality factor. That means take this bandwidth here, take the center frequency here, and that measurement yields immediately the unloaded quality factor that you want. Now you may naturally ask now, how exactly do I achieve that? Meaning, how exactly do I achieve my S21 to be much less than 1? Well, the way you achieve that is by designing this circuitry to have weak coupling. Let me go back to the circuitry so I can show you this. See, you're the one who's choosing these numbers. You're the one, in other words, that decides how much energy you coupled from the input to the resonator. So you want this to be very weak. You want to barely tap the resonator with energy. You want to barely excite the voltage here and barely get measurement out, because in that case your S21, which of course measures the amount of power you transfer from the input to the output, will actually be much less than 1. So even though for your actual filter designs, you know the coupling sections because they're coming from your Chebyshev and the J equations and everything else we have discussed, when you make a circuitry to measure the quality factor of your resonators, you must make the circuit such that this is weakly coupled. And so when you make a measurement here, what will happen is, once again, your S21 will appear something that is that low. But that's not because the resonator is bad, that's because you purposely designed this to have a weakly coupled section. Or if you want to say it in different words, you have purposely mismatched the filter. So the loss that you see here, so again, this may be the 0 dB line, and you may be down to the negative 20 dB line, that loss that you see is not ohmic loss, it's just mismatch loss. And you know that you can fix that quite easily when you make the real filter by simply matching the circuit, by simply fixing the coupling from weak to strong, which is something that will happen when you do the filter. But once again, when you measure the resonator, you barely tap the filter. The mechanical analog to this is that if you have a mechanical resonator, let's say you have a bell, and you're trying to basically measure the quality factor of this bell, you're not going to take a huge hammer and just hit the bell and excite it with very strong externally provided energy. You're just going to go and barely tap it. So the resonance of the bell is not really influenced by your tapping. It's only influenced by the actual bell quality. If you hit it with a very strong hammer, the resonance is actually influenced by the hit itself and not only by the bell. So let me give you an example. This is a real circuit, a real measurement that I basically took from a reference that you will see later on from a PhD at the University of Michigan. The resonator that they were building here is this substrate integrated cavity. So you can see that we basically have a substrate. In this particular case, this was silicon. And the silicon was basically etched away to create an air cavity here. And this air cavity has been plated with metal. And essentially, we have an air cavity to trap an electromagnetic wave. That's the substrate integrated miniaturized cavity that I discussed before. We are designing a very weak coupling section here, given by this microstrip feed line. So there is this microstrip feed line here that essentially will induce a wave to excite this cavity. And you're ensuring that this is a weak coupling by opening a small slit here, a small slot, to allow for this energy to come into the cavity, but again, a very weak amount of coupling. So this is the layout of the resonator, and this resonator was designed around 30 gigahertz, and sure enough, if you measure the S21 of this, you will basically find out that we have a weak coupling section here, and if you apply the equations that I discussed with you before, you will basically find out that you have an unloaded quality factor of 1617 simulation and 1422 in measurements. In this picture that you see here, I don't show you the output, but there is obviously another output line here with exactly the same slot that basically the energy goes. So in other words, the energy comes from the input, it weakly couples in and basically comes out, and this is the S21 measurement that we're making here.